Math 287, Cuesta College. I'm Joe Vasta, and today we are covering section 2.4, REF and RREF. And here are some problems that we're going to do, but before we do these problems, we should go to our definition sheets and see what these are abbreviations for REF, RREF. So let's take a look. See what we have here. So REF stands for row-echelon form, and a matrix is in row-echelon form if it has these three conditions. If there are any rows consisting entirely of zeros, they are grouped together at the bottom. The first non-zero element of any non-zero row is 1. Call the leading one. And the leading one, condition number 3, the leading one of any row below the first row is to the right of the leading one of the row above it. Now, if we just said, okay, that's what it is, and moved on, this really wouldn't stick, so we're going to be looking at examples. Then we have the rank is our next definition. The number of non-zero rows in a row-echelon form matrix is called the rank of the matrix. Okay, we're also going to hit you with the next definition, which is RREF, which I guess we can put right here. So a matrix in reduced row-echelon form has conditions 1, 2, and 3, which are these conditions here. The matrix is in REF. And another condition, it says any column that contains a leading 1 has zeros everywhere else. Okay, so this is a lot to grasp just by looking at the definitions of these two things here, a matrix that's in REF and a matrix that's in RREF. So the best way to get this is to look at particular examples, and as we go through about 6 examples, this will start clicking, okay, in terms of these conditions. So let's take a look at the conditions, and then let's took this sheet here. So, you know, hopefully you'll have your definitions right in front of you. Maybe you've printed them out. Our questions here, and this is what you get in your homework, and this is what you would get on the test as well, is the matrix in REF, is the matrix in RREF, and then find the rank of the matrix. Condition number 1 says, if there are any rows consisting entirely of zeros, they are grouped together at the bottom of the matrix. And look, we have a row that is all zeros. We can call that a zero row, and it's at the bottom of the matrix. So condition 1 is satisfied. So, you know, we have condition 1. I'll put a little check mark there. Condition 2, it says the first non-zero element in any non-zero row is a 1. So how many non-zero rows do we have? We have 2 rows, and we have 1 non-zero row. And that non-zero row, its first non-zero element is a 1. So in terms of condition 2, that's also satisfied. Okay. Condition 3, it says the leading 1 of any row below the first row. Do we have any leading 1s below the first row? And the answer is no. So if we have a condition, you know, condition 3, it talks about leading 1s below, and we don't have any leading 1s below, then that condition is automatically satisfied. So condition 3 is satisfied as well. And once again, I don't think this first example is going to set things straight in people's minds, so that's why we're doing 6 examples. Condition number 4 says any column that contains a leading 1, how many columns do we have that contain leading 1s? Well, how many leading 1s do we have? Just that leading 1. Any column that contains a leading 1 has zeros everywhere else. And that is true as well. So in terms of the first question, is the matrix in REF? The answer to that is yes. It is, because it meets the first three conditions. Is the matrix in RREF, or reduced row echelon form? Well, it meets all four conditions. Yes. Now the rank is the number of non-zero rows in row echelon form, and we have one non-zero row in this matrix, so the rank is 1. So yes, yes, 1 is the answer to problem number 1 in terms of asking about row echelon form, etc. Let's go ahead and do problem number 2. Okay, so we have to go through these conditions. If there are any rows consisting entirely of zeros, do we have any of those? Yes, the top row. Then they are grouped together at the bottom of the matrix. Well, that 0 row is at the top and not at the bottom. So condition number 1 fails. Okay, I'll put an X near that. Which means, for your matrix to be row echelon form, it has to satisfy the first 3 conditions. So the answer is no, it's not REF. And then if it's not REF, it's definitely not going to be reduced row echelon form, so no for the second question. And the third question says find the rank of the matrix. Well, the rank, the definition that we got, it says the number of non-zero rows in an REF matrix is called the rank. This is not an REF matrix, so in terms of the rank, we don't know how to do that yet. So we're going to put a question mark, and we'll come back to how to find the rank of a matrix that is not in REF. Now, this stuff seems very abstract in terms of, like, who cares about row echelon form and reduced row echelon form, but it's going to help us in linear algebra, help us solve linear systems, etc. Okay, so here are the other 4 problems. Problem number 3. Okay, we're going to go ahead and check these conditions. 1, 2, 3, 4. The 4 conditions. Condition number 1. Do we have any rows entirely of zeros? The answer is no. The first row is 1, 0, and the second row is 0, 1. So we don't have any 0 rows, but it says if we had any, they would be grouped together at the bottom. Well, because we don't have any 0 rows, condition 1 is actually satisfied. Okay. Condition number 2, it says the first non-zero element in any non-zero row is 1. So let's go ahead and look at the first non-zero element in row 1. It is a 1. The first non-zero element in row 2, so the first non-zero element in row 2 is a 2. Condition 2 says that those elements have to be 1s, and this one being a 2 makes it so condition number 2 is not satisfied. Okay, so it has to meet the first 3 conditions for your matrix to be in row echelon form. And so we don't need to continue checking the other conditions. We are going to say no, it's not in row echelon form. No, it's not in reduced row echelon form. And what's the rank? We don't know. An unsolved problem in math. Actually not. We'll figure that out. Okay, let's go ahead and do matrix number 4. Okay, so there are 4 conditions. Let's check them. If there are any rows consisting entirely of zeros, do we have any 0 rows? No, we don't. Then they are grouped together at the bottom of the matrix. Well, we already have if false. If false is true, so the condition number 1 is met. It's satisfied. So we put a check there. Condition number 2, it says the first non-zero element in any non-zero row is a 1. I'm going to go ahead and circle the first non-zero element of each row in colors. So the first non-zero element of row 1 is a 1. The first non-zero element of row 2 is a 1, and the first non-zero element of row 3 is a 1. So condition number 2 says those things that I circled or boxed have to be 1s, and those are called leading 1s, so condition number 2 is satisfied. Condition number 3 says the leading 1 of any row below the first row, so it looks like we're going to have to check 2 rows, 2 leading 1s. So the leading 1 of any row below the first row is to the right of the leading 1 of the row above it. So let's take a look at this one right here. This leading 1, is it to the right of the leading 1 that's above it? And yes, it is. It's over this way. Now, is this leading 1 in row 3, is that to the right of the leading 1 above it, in the row above it? And no, it's directly below, so condition number 3 is not satisfied. And we don't care about condition number 4 because now we know that this is not row echelon form. It's certainly not reduced row echelon form. And in terms of the rank, we don't know how to do that yet. And so no question mark. Let's go ahead and take a look at matrix number 5, or problem number 5. So I have 4 conditions that I have to check, or check each condition until we get one that fails. And then we'll answer our question. Condition number 1, are there any rows of zeros? Were there entirely zeros? No. So condition number 1 is satisfied. Condition number 2, go ahead and box the first non-zero entry of each row. Well, look at these. They are both 1s, so condition number 2 is satisfied. Condition number 3 says the leading 1 of any row below the first row, so there's only one that I have to check, is that to the right of the leading 1 in the row above it? Yes, it is. So condition number 3 is satisfied. That would mean this matrix is in row echelon form, so the first question where it says, is the matrix in row echelon form, we would say yes. Condition number 4 says the leading 1, wait, no, it doesn't say that. It says, condition number 4 says, any column that contains a leading 1 has zeros everywhere else. So let's check out this column right here. I've just lost part of my pen here. So I'm going to go ahead and put a green circle around each of the columns that contain leading 1s. So it says the column that contains the leading 1, each of the columns has zeros everywhere else. So there's a 0 there, so that first column's good. This column that contains this leading 1 should have a 0 here, but it doesn't. It has a 3 there, which means condition number 4 is not satisfied. So this matrix is not in reduced row echelon form, RREF, so we give that a no. The rank of a matrix is the number of non-zero rows in a row echelon form matrix. This is row echelon form, and how many non-zero rows do I have? I have 2 non-zero rows. That is the rank of the matrix. So you may have already realized from example number 1 and example number 5, where we were able to get a rank, that the rank is always going to be less than or equal to the number of rows your matrix has. Let's go ahead and do number 6. Here are the 4 conditions. Well, there's just 4 numbers there. Let's check them. If there are any rows consisting entirely of zeros, well, we don't have that, so that's satisfied. The first non-zero element in any non-zero row is a 1, and it looks like we have that. So condition number 2 is satisfied. Condition number 3 says the leading 1 of any row below the first row is to the right of the leading 1 of the row above it. So look at this. Here's a leading 1 that's below the first row, and it's to the right of that leading 1. So this matrix is in row echelon form. So we have a yes for that question. Condition number 4, it says any column that contains a leading 1. Whoa. So let me go ahead and circle the columns that contain leading 1s. So it says each column that contains a leading 1 should have zeros everywhere else. Well, we have a 0 there, and then on this one, we have a 0 there, so this one is satisfied. Which means this matrix is not only in row echelon form, REF, but it's also in reduced row echelon form, which is RREF. So we say yes to that. The rank of this matrix is the number of non-zero rows if the matrix is in REF, and so it looks like there's 2 non-zero rows. Yes, yes. 2 is the answer. And so hopefully these conditions that we went over, where we have condition 1, 2, and 3, and it's on your definition sheet. And then condition 4, it doesn't really mean much when you just read the conditions. You actually have to do what we did and go over several examples to see, oh, sometimes these conditions are satisfied and sometimes they are not satisfied. So we are going to jump briefly into PowerPoint to sort of derive something about linear systems, and then we'll come back, and most of this lecture will be me writing on the piece of paper. So let's take a walk down memory lane and remember what happened maybe in an algebra class when you were given 2 equations and 2 unknowns, x and y. And we're going to go ahead and solve this system. I know we learned about augmented matrices, but we'll come back to that topic after we solve this. Look at that last equation. That last equation, 5x plus 10y equals 20, it's a little inflated. We can scale it down if we multiplied both sides of that equation by a 1/5. So that's what I'm going to do. And when I do that, I end up getting this system here. But this system is actually the same as the top system, because multiplying an equation by a non-zero number does not change the solution. Okay, so that's one thing we can do. We can multiply an equation by a non-zero number. Let's go ahead and continue this. There's something that we can do with those equations. I don't like this 3x minus 4y equals 2 on the top. I'd rather have it on the bottom. So the question is, could I interchange those equations? Is that going to mess up the solution? And the answer is no. We can interchange 2 equations. So there's actually 2 rules we have now. We can multiply an equation by a non-zero number, and we can interchange 2 equations. Now, this is going to be the heart of solving linear systems, is I want to get opposite coefficients in front of the x's so I can add the equations together. So to get opposite coefficients in front of the x's, I'm going to multiply the top equation by -3. When we do that, we end up getting this equation here. And so after I do that, I can add those equations together, and I'm going to get rid of the x's and have just what? -10y equals -10. So that's my third thing that I can do with a system of equations. I can add a multiple of one equation to another, and that's what we have done here. This is called elimination. And now I can solve this system. Let's see, on the last one, I'll divide both sides by -10, or multiply that bottom equation on both sides by a -1/10. When I do, I end up getting y equals 1 on the bottom, and then the top equation is just what it is. And so I can plug y equals 1 into that top equation and get x plus 2 equals 4, so x is going to equal 2. And we write our answer as an ordered pair, 2, 1. Okay, so some of you are like, wow, that was extremely boring. It is. You're in a math class. Well, you should be saying that. But the three things we can do is multiply an equation by a non-zero number, interchange two equations, and add a multiple of one equation to another. And so now we're going to show you what this system looks like, the original system, in terms of the augmented matrix. There's the augmented matrix. Now, instead of doing all these operations and always writing x's, look at how inefficient this is. Look, 3x, 5x, and there's an x and 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 an x. With the augmented matrix, I don't have to write x. I just remember that the first column, that's the coefficient of the x's, and the second column is the coefficient of the y's, and the third column is the right-hand side vector that we were talking about in an earlier section, and that's just 220. So what I'm going to do is I could actually work on this matrix, and instead of in these statements multiply an equation by a non-zero number, I can look at the statement as multiply a row by a non-zero number, interchange two rows, and add a multiple of one row to another. Those are called elementary row operations, and if you do that, you end up getting this augmented matrix. And if you just did it using the matrix, you can get the problem done and then write out the equation. See, that says x plus 2y equals 4, which is really over there. And then the bottom one says y equals 1. Now, some of you might think, why would you do this? Because your system might be like a 3 by 3 or a 5 by 5, and there's no way you want to be doing all this stuff. You'd rather just work with a nice, clean augmented matrix and do three kinds of elementary row operations to get your matrix into a form that you can actually solve the system. Here's the other thing that's sweet about this. This matrix right here is in row echelon form. So it's in REF. Now it's not in RREF because of that 2 there, but it doesn't matter. We have an REF augmented matrix where this matrix right here is not REF. So that's something to ponder. Like, why is that important? So we're going to get back to the non-PowerPoint part of this lecture. So we'll go back to the definition sheet, and here is the definition we already saw, RREF. So our next definition is definition of elementary row operations, and there's 3 of them. Interchange rows. Now there's some machine language right here, which looks like that. I don't know why it's not all justified. Oh well. So you don't have to worry about this RI, RJ with the arrows. I will do that a few times, but you don't really need to do that to do your homework or to take a test. So interchange rows. I think that was the second thing we did in the PowerPoint. Multiply a row by a non-zero constant. Okay, and there's some machine language there. And add a multiple of one row to another. And so that's kind of the machine language there. So if this confuses you, just ignore it for now. And then here's the other thing, Joe's non-elementary row operation. And I will sometimes use this to make things simpler, so I don't have to work with lots of fractions within my matrix. And so this is where we add a multiple of one row to a multiple of another. And then we replace one of those rows with the result. And this is just putting 2 of these elementary row operations together. So this is not an elementary row operation. That's why I call it non-elementary row. And I will let you know when I am doing this. But it really does help me become more efficient and try to avoid some fractions. So the next several examples we will do will involve row operations on matrices. So example number 1, what they'll tell you to do in your homework is they will tell you to reduce to REF and find the rank. It's just what they say. So reduce, it just means do row operations. It doesn't mean we're changing this to reduced row echelon form. We are just reducing this to row echelon form. So it's a little confusing, they're using that word, but that's what a lot of linear algebra books do. And then we can find the rank. So what is up with that? We'll go ahead and do that, and then we'll show you some definitions and theorems that can help with understanding this. So what I want to do is I want to put this in row echelon form, and that's kind of a crazy thing to do if you're not used to matrices. I see a 1 down there, and I'd like that 1 to be on top where the 3 is. So what I'm going to do is I'm going to interchange row 1 and row 2. Okay, and that's one of my row operations, interchange rows. And so when I do that, I'm going to have a 1, 5, and then on the bottom I'm going to have a 3, -2. Okay, so these two matrices are not equal. Okay, so they are not equal, but they are row equivalent. So instead of putting an equal sign, because I cannot use an equal sign, I'm going to go ahead and put this little sign right here, which means these matrices are row equivalent. Now, what did I do to get there? Here's the machine language that we saw in the definitions. I went ahead and I had row 1 and row 2, and I interchanged those rows. Your book is going to have a different notation for row operations. It's not going to affect you if you just do your homework. I think this machine language that I use is a little clearer for me, okay? And I've seen this in other linear algebra books. So I'm going to interchange row 1 and row 2. Okay, now the next thing I want to do is this. Here is a leading 1. And if I'm going to have a leading 1 on the row below, I do not want it right below. I'd like a 0 below that leading 1. So how do I get a 0 below that leading 1? I want to put opposites there. And to put opposites there, I'd like to multiply row 1 by a -3. And then I want to add that result to row 2. So this is what I'm going to do. I'm going to put a little temporary row 1 right below my matrix. So look at this. -3 times 1 is -3. -3 times 5 is -15. Okay, so this is temporary row 1, and here is row 2. I'm going to add those together, and that's going to become my new row 2. So I have a 1, 5, 0, -17. What just happened in terms of the machine language? I went -3 times row 1 plus row 2 becomes the new row 2. Now some of you might be wondering, couldn't you have written an intermediate matrix that looked like -3, -15 for the first row and 3, -2 for the second row? Yes, you could have done that, and then you could have added row 1 with row 2 and got this result, but then you would have to scale down row 1 again. So that is what we've done. This is adding a multiple of one row to another. Okay, so this is one of the elementary row operations. The question is our matrix in row echelon form? Well, we don't have any rows of zeros, and we have a leading 1 there, but we do not have a leading 1 right here. The first non-zero entry of this row is a -17. So what should we do with row 2? Well, multiply it, scale it down, multiply it by -1/17. It's not going to affect that 0 there. And so what does this give us? This gives us 1, 5. That stays the same. And the bottom is 0, 1. Okay, so we have no rows of zeros. First non-zero entry in each row is a 1. And if there's any leading ones below the first row, they're to the right of the leading one above it, and that's correct. So what do we have here? We have our answer. We have just reduced this matrix to row echelon form. Now this answer does not equal our original matrix because it would have to be identical for it to equal it, but it's row equivalent, and that's going to help us do a lot of things. The other thing that we want to say is, well, what is the rank? The rank of this matrix here is 2. So here's a theorem about rank, or maybe we can call it a definition, is the rank of a matrix that is not in row echelon form can be found by reducing it to row echelon form and finding the rank of the row echelon form matrix. So like if this matrix here was called A equals this matrix that's not in REF, then to find the rank of that matrix, rank of A, you look at the rank of the row echelon form. And so the rank is 2, and that completes the problem. So we'll do a few more of these problems. So in your homework, they're going to expect you to reduce matrices to row echelon form. Some of you might say, what about reduced row echelon form? We'll get to that, okay? We just have to take baby steps to get there. Okay, I think we should really look at some of the theorems here. What do we have? Let A and B be 2 matrices. B is row equivalent to A if and only if, that's what the IFF stands for, if and only if B can be obtained from A by a finite sequence of elementary row operations. So row equivalence is kind of what we were saying, you know, and we have this special sign here, not an equal sign. B is row equivalent to A. So look what we have here. This matrix A is row equivalent. We can call this matrix B, it's row equivalent to B. Now here's the theorem here, which we're not going to prove. Every matrix, including the one we had here, can be reduced to row echelon form. Okay. So this is good because if you're doing your homework and they say reduce to row echelon form, you're not going to be like, well, maybe this is one that has no solution or cannot be done. No, any matrix or every matrix can be reduced to REF. Definition. If B is row equivalent to A, then their ranks are the same. And that's kind of what we were saying right here. See, the rank of A, our original matrix, is 2, and the rank of this guy is also 2. And that's just the definition of rank. So we finished the definition of rank because now we can do the rank of any matrix. So any matrix can be reduced to REF, and that's how you can find its rank. And theorem. To find the rank of any matrix A, so this is just sort of the procedure, what we did. Reduce A to REF and find the rank of the reduced matrix. And that's pretty much what we did here. So we reduced it and said the rank of that is 2, so the rank of A is also 2. And so those definitions and theorems, remember, you don't have to memorize these word for word. These will help as you do your homework. And I know it's overwhelming to have 20 pages of theorems and definitions in linear algebra, but linear algebra does have a lot of that stuff. So let's continue to do these problems where the instructions are reduced to REF and find the rank. So here is the next problem here. Okay. So, what am I going to do here? The deal is you want to look at the first column and see if that first column has a 1 in it. Now there are times when you will not find a 1 in the first column, and we'll address that as we do more of these. But there's a 1 there, and that's put pretty much in a good position. That is put right on top. If that row 1, 2 was on the bottom, then I would interchange 2 rows. So I want to call that 1 my pivot. And I'm going to use this pivot to put a 0 in that position where the 2 is, and to put a 0 in the position where the 3 is. So let's work on row 2. I want to put opposites right in those positions. So I would like to multiply row 1 by a -2. And I'm going to put temporary row 1 right below this matrix. So to do that, I end up getting -2, -4. I'm going to add that to row 2, and that will give me my next matrix here. So I have 1, 2, and then look, I'm adding those together. 2 plus a -2 is 0, that's what I want. And 5 plus a -4, so 5 minus 4 is 1. Now do not put that last row, because I'm going to show you how to become even more efficient. The machine language, which is really not necessary when you're doing your homework, is this. I went -2 times row 1 plus row 2 gives me the new row 2. Okay, now I could put the 3, 2 there as if I want, but I'm showing you how to become more efficient. So I've used my pivot to put a 0 there. Let's use the same pivot to put a 0 where the 3 is. So I need opposites right here where the 1 is and where the 3 is. So I'm going to multiply row 1 by a -3. And so modified row 1 will be -3, -6. Okay, so there's the modified row 1. And I'm going to add that to row 3. Now this is where it really helps to have this on video, because you can pause the video at any time and think about what I'm saying. So what we have is when I add those 2 green things that I circled, I have 3 minus 3, which is 0, and 2 minus 6, which is -4. Now, a lot of teachers would actually have written an intermediate step. They would have written the matrix 1, 2, 0, 1, 3, 2. And then made the jump to this one right here. In machine language, what did I do? I went -3 times row 1 plus row 3 gives me the new row 3. Okay, so look at this pivot, this leading 1 has zeros beneath it, which is good. That's what we want. We don't want a situation where we have another pivot that's right below this pivot, because row echelon form says your pivot ones, the ones below have to be to the right of the one above. Okay, so now what I'm going to do is I'm looking at row 2, and I see this one right here. I'd like to now use that as a pivot to try to take care of that -4. And how do I do that? Well, what I'm going to do is I want opposites there. So I'm going to multiply row 2 by a 4. When I do that, I'll put temporary row 2 right below the matrix, so 0, 4, and I'm going to add those guys together. So look what I have. 1, 2, 0, 1, and then look, 0, 0. My machine language for this is 4 times row 2 plus row 3 gives me the new row 3. So let's check to see if our matrix is in row echelon form or if we have to do more stuff. If there's any rows of zeros, they're at the bottom. Okay, so condition 1's good. The first non-zero entry of each non-zero row is a 1. That's good. And any leading ones below the first row should be to the right of the leading one above it. That's good. And so what we have here is we have our answer. That's our matrix. It's in row echelon form. It's equivalent to our original matrix. We can call our original matrix A. If you want, you can call that B. So A does not equal B. A is row equivalent to B. And they want to know what the rank of our original matrix is. The rank of A is, well, what's the rank of this guy? You count the non-zero rows. 1, 2. So the rank of A is also 2. And that completes this problem. Okay, so you might have noticed in this one that there's probably some sort of algorithm for taking a matrix and reducing it to REF. So let's go over this algorithm, and I'll show you this. It's on the definition sheet, and you're going to see we kind of did that here. So let's just see what we have. Reducing a matrix to REF. Go to the leftmost non-zero column. And that's what we did here. So we went to that column. Find a pivot number, desirably 1, and move that row to the top. Well, in example number 1, that row was already at the top. Our pivot 1 was at the top. In the last example, example 1, we had to interchange 2 rows. And then look at this. This is not very technical here, but I'm going to do it anyway. Force zeros below the pivot by using row operations. Now, isn't that what we did? We used row operations and forced zeros into those positions. Okay, let S be the submatrix below the pivot. Repeat the above process on S. So here's a matrix S. I'm seeing if I have, can't find what I'm looking for here. I'll just use yellow. So this right here is a submatrix. We could just say 1, -4 is the submatrix, and then repeat the above process on S, and then at the end scale each non-zero row so that each pivot becomes a leading one. Now your book's going to tell you a different procedure. They really want each pivot to be 1. I'm saying you don't really need that, and they will turn entries into the matrix into some of the ugliest fractions you've seen. We don't need to do that, and that's why I say scale your pivots at the end if it's going to cause some ugly fractions. So before we do the next example, let me go ahead and just kind of show you a diagram with a more complicated matrix here. And this is just what we do here. So there's our pivot, and we put it up at the top by interchanging 2 rows, and hopefully our pivot's a 1. Then we use our pivot to force zeros for every other entry below the pivot. When you're done doing that, then I'm going to write this a little differently. This matrix right here, so if you get rid of the row in the column that has the pivot, this matrix I'll call S, and then you repeat the procedure on this. We call it a submatrix because it's part of this matrix. You proceed to repeat the process on S, and then you just keep going until you're done. And I know you're like, wow, that's a big matrix. But the next one we do will be bigger, but won't be like this big. So let's see if we can do this. Okay, so let's get rid of this. and do this one right here. Problem number 3. And what do we have here? We have this pretty big matrix. It is a 3 by 4, and we are trying to do the instructions that say reduce to REF and find the rank. So my first task is to reduce this to REF. So if you look at your first column, you notice that you do not see a 1 there. So that's not the end of the world. What I'll do the first time I do this problem, I'm going to do this problem twice. What I'm going to do the first time I do this problem is I'm actually going to try to be clever to get a 1 somewhere. So I see a 3 here and a 2 here. So I could actually go 3 minus 2 gives me 1. So like the machine language on this would be R1 minus R3 gives me the new R1, the new row 1. So I'm going to be very careful about this and make sure that I kind of go slowly here. So row 1 minus row 3, so that's 3 minus 2 is 1. Negative 1 minus 2 is negative 3. 1 minus a negative 1 is 2. And 8 minus 6 is also 2. And everything else in this matrix I'm going to keep the same. So 3, 1, 1, 16, 2, 2, negative 1, 6. Now, did we have to do that? No. Could I have used this 3 as a pivot? Absolutely, and I'll show you that after I'm done with this problem. That's why I said I'm going to do this problem twice, because as much as I hate doing the same problem twice, I think it's very important in this one. So we have a 1 there, and you know, for a lot of people, that makes a lot of people happy, because now we can force that to be a 0 and force the 2 to be a 0 as well. So let's work on forcing the 3 to be a 0. I'm going to multiply row 1 by a negative 3. That's going to put opposites in those positions, and I'm going to write temporary row 1 beneath this. So this is going to be negative 3, positive 9, negative 6, negative 6. I'm going to add that row to that row. And so let's do that. 1, negative 3, 2, 2. And I have 0, 10, negative 5. Now, how did I get the 10? I went 1 plus 9, and then negative 5, I'm going 1 plus a negative 6. And then 16 plus a negative 6, or 16 minus 6 is a 10. Okay, now I'm going to do that little trick I did on an earlier example where I don't write the 2, 2, negative 1, 6, though. If you're feeling a little insecure, you can do that and do an extra step. What I'm going to do is I'm going to now use this pivot, and use a different color, of course, to get opposites in this position here and where the 2 is. And so the number I'm going to multiply row 1 by would be negative 2. I'll use purple. Hopefully that's obvious. Now before I do that, my machine language for this last step was minus 3 row 1 plus row 2 gives me the new row 2. Okay, so let's continue. I also noticed, maybe on this last example, and I'm not going to go back and edit the video, I'll show you like this, the perfectionists out there noticed I did not write machine language for this. So the machine language for problem number 1 on this step, when I multiplied row 2 by a negative 1 over 17, was negative 1 over 17 times R2 gives me the new R2. So there that is. It's written down there now. And I'll try to keep writing the machine language, but I won't always write it. Okay, I'm going to stop doing that after a while. Okay, so I'm multiplying row 1 by negative 2, and I end up getting negative 2. Negative 2 times negative 3 is 6. And then I have -4, -4. So you can see that it's probably be pretty simple to make an arithmetic mistake, and if you make one pretty early on, it's gonna propagate through your matrix, and it will be bad. So -2 plus a 2 is a 0. 6 plus 2 is 8. -4 and a -1 gives me a -5. And a -4 and a 6 is a +2. The machine language for that was -2 times row 1 plus row 3 gives me the new row 3. I have a pivot here, and it's a 1. I'm done with that pivot. I have this submatrix right here, and that's what I'm going to be focusing on. I want to put that in row echelon form. It's almost like this could be its own separate problem right here. Okay, what do we notice about one of these rows here in this yellow matrix here? Well, the top row can be scaled down if I multiplied it by a 1/5. And so that's what I'm going to do. I'm going to multiply row 2 by 1/5. And so, got to get another piece of paper here. I'm going to keep the top row the way it is. 1, -3, 2, 2. Then I have 0, 2, -1, 2. So I just multiplied row 2 by 1/5. And then the last row, row 3, there's no way I can scale it down. So I have 0, 8, -5, 2. What did I do? I went 1/5, row 2 becomes the new row 2. And that's what we did. Multiplied a row by a non-zero number, and now we have this. Let's just kind of put this up here. We have that. Now your book's going to be very concerned, so we're kind of focusing on this right here. Your book's going to be very concerned with making the pivots a 1. They're going to be so concerned, sometimes they'll say, well, we should have, in the last example, multiply it by 1/10. So we would have had a 1 here, a -1/2 there, and a 1 there. I don't like that. You're going to get the same results using the method that I use, and you won't have a whole bunch of fractions within your intermediate steps. So what I'm going to do is I'm going to use that 2 as a pivot, because I can. I just want to get opposites there, and I'm going to multiply row 2 by a -4. You do that, you'll end up having a -8 there and a +8 there. So my temporary row 2 is going to be 0, -8, +4, because I have -4 times -1, and then we have -8. I'm going to add this to row 3, and that's going to give me my new row 3. So -4 times row 2 plus row 3 gives me the new row 3. So let's see how this is going to work out here. We have 1, -3, 2, 2, 0, 2, -1, 2. Okay, so those are unchanged. And then what do I have? I have 0, 0. This guy right here is going to be -1, and this is -6. Okay, so now I have, here's a pivot, here's a pivot, and then this guy right here, I mean, we're not going to call him a pivot, but I guess he could be one. These are just the first non-zero entries in each row. And for this to be row echelon form, we want those 3 things to be 1s. And the third condition where this one's to the right of that one, that's correct, and this one's to the right of that one, that's correct. We just need to make that into a 1 and that into the 1. So what I'm going to do is I'm going to multiply row 2 by 1/2. So yes, in the end I am going to have fractions, but I'm not going to be doing much arithmetic on the fractions because I'm getting to the final answer. Multiply the last row by a -1. Okay, so what we end up getting is we have 1, -3, 2, 2, 0, 1, -1/2, 1, so that's multiplying row 2 by 1/2, and then multiplying row 3 by -1, we have 0, 0, 1, 6. And so that right there is our final answer. Look what we have. We have leading 1, leading 1, leading 1. You can check all the conditions of REF. It is REF, our first matrix. If we'd like to call that matrix A, we can see that the rank of A is going to be 1, 2, 3 non-zero rows. So the rank of A is 3. Now, in the thing that I boxed is not matrix A, it's not equal to matrix A, we can call that matrix B, but the rank of our original matrix is 3. And so yes, this seems like we're doing a bunch of worthless bookkeeping here, but we're not. This is going to help us throughout linear algebra, and we'll even be doing row operations in the differential equations part of this class. Okay, so I did say I was going to do this problem 2 times, and now I'm going to do it the second time. And I know some of you are like, yep, I'm skipping ahead on the video, but you might want to see some of the things we do. So this is, well, actually, I had planned to do that. So look, 3 again. Okay, so I don't need that piece of paper. And so notice it's the same problem here. Look, 3, 3. Yes, hopefully I wrote it down correctly. And we're going to do row operations. I'm going to say, now when you're doing your homework, or especially when you're doing the test, don't do the problems like 2 different ways. I mean, once you've finished the problem, move on to the next problem. But I want to show you that I can use that 3 as a pivot, and the first thing that I'm going to do is I'm actually going to go row 2 minus row 1. Okay, so I'll write that. Row 2 minus row 1 gives me a new row 2. So you could say I multiplied row 1 by -1 and then added that to row 2. Maybe I should have said that. And so what does this give me? So I'm going to keep row 1. I like that for row 1. 3, -1, 1, 8. I don't want my row 1 to have a 16 in it. And I'm going to go ahead and subtract. So I have 3 minus 3 is 0. 1 minus a -1 is 2. And then we have 1 minus 1 is 0. 16 minus 8 is 8. Okay, because we're doing this weird thing, I'm going to go ahead and write out row 3 without trying to do too many steps within one thing. And so that's what we did. We just did row 2 minus row 1 gives me the new row 2. We have that. Now what I'm going to do is I'm going to use this 3 as a pivot. And you might be saying, well, this is Joe, you're going to have to do fractions. But no, watch this. I want opposites there. So I'm going to multiply row 1 by a 2, which will give me a 6th in that position. And I'm going to multiply row 3 by a 3, which will also give me 6 in that position. So I want a 6 and a -6, so I'll put this as a -3. Okay, so here's modified row 1. It's going to be 6, -2, 2, 16. And modified row 3 is going to give me -6, -6, +3, -18. I'm going to add those together. That's going to become my new row 3. This is what we were referring to as a Joe operation. It's just doing a few elementary row operations in one step. So I'm going 2 times row 1 minus 3 times row 3. This gives me the new row 3. That is what I'm doing. So let's see if we can write this down and not have any mistakes here. Row 1 I'm keeping the way it is. So I have 3, -1, 1, 8. Row 2, I'll just keep it as 0, 2, 0, 8. And row 3 now becomes, okay, so let's do this. 6 minus 6 is 0. And then over here we get -8, 5, and this is -2. Okay, so look what we have. We have my pivot, which I understand it's not a 1, and I'll change it to the 1 at the very end, and I have zeros below that. Thus proving that we can do problems this way. We don't have to be really rigid like the book asks us to be. It's good to be rigid in math, but like in terms of when you have some choice, some independence to do things that are legal, we can do this. I'm going to go ahead and use that 2 as my next pivot. And I know some of you are like, scale down row 2, but I don't have to. I'm not going to do that right now. I'm going to go ahead and multiply row 2 by a 4, getting an 8 there, and we have a -8 right below. So watch this. I have 0. This is modified row 2. So 0, 8, 0. 8 times. Maybe I should have scaled it down, but I mean, I would think I would have still had the same problem here. So this is 32. Okay. So let's go ahead. I think I do need that piece of paper now. Okay, so this is row equivalent, great, row equivalent to 3, -1, 1, 8, then I have 0, 2, 0, 8, and then I have 0. Now I'm adding these guys together right here. So this gives me 0, 0, 5, and then 30. So here are my I'm going to call them pivots, but they're the first non-zero entries of each of the rows. And 1's a 3, 1's a 2, 1's a 5. So what I'll do is I'll multiply things. Okay, let's write the machine language. Here we have, what did I do? I went 4 times row 2 plus row 3 gives me a row 3. Then on this one I'll multiply first row by 1/3, the second row by 1/2, and the third row by 1/5. And so let's see what it gives me. We have 1, -1/3, 1/3, 8/3, and then the next one's going to be 0, 1, 0, 4, and then the last one's going to be 0, 0, 1, 6. And so here are my leading ones. You can see that this satisfies the 3 requirements for row echelon form, and I have my answer right here. Before I say anything else, I should actually put what happened. I went 1/3 row 1 becomes the new row 1, 1/2 row 2 becomes the new row 2, and 1/5 row 3 becomes the new row 3. Some of you are wondering, well, on the other one that you did here, you didn't write that down. So I'm going to go ahead and write that down on this one here. I know this is probably confusing to some people seeing what I'm doing here. This is just when I did this problem the first time. I didn't write that down. Okay, so looks like we have this. The rank of our matrix, rank of A, is the same as the rank of this one, which is 3. So if you've been kind of paying attention, like in terms of what's been happening, something's really going to freak you out. Is the fact that we did this problem twice now. And look at our answer the first time we did the problem. Our answer looked like this. And then the second time on the same matrix, our answer looked like that. So that's very disturbing in math when you do the problem 2 different ways and you did it legitimately both ways and you end up getting answers that are not identical. Well, this is legitimate, what we did, but I'm going to write out a statement here. Row echelon form is not unique. Okay, so that's a bummer. And we'll address what to do when you're doing your homework and you can't, you get an answer and it does not match the answer in the back. Did you do it wrong, or did you just get one that was different than the way the book people did it? Okay, well, that is a little disturbing that REF is not unique. We'll deal with that. But what we want to do now is we want to take this same matrix, this matrix that we've been calling A, and now we want to reduce to our REF. Okay? So to reduce this to our REF, let me go ahead and write down, trying to think of what I need to do here. I'm going to write down this matrix, maybe the one right above it. Okay, so this is exactly the matrix we did in problem number 3, and we did problem number 3 2 times. So I'm going to go ahead with the one that I did. The first thing you want to do when you reduce it to reduced row echelon form, so it says reduce to reduced row echelon form. Your first step is put it in row echelon form. And so we did. So I'm going to just kind of copy down what I did on the other piece of paper. I have 1, -3, 2, 2, 0, 1, -1/2, 1, 0, 0, 1, 6. So this is from the last problem. From problem 3. Okay. Now, if I were to do this and it didn't ask me to put it in just regular row echelon form, I would have actually written this. I would have written 1, -3, 2, 2, and then 0, 2, -1, 2, and then 0, 0, 1, 6. Okay, so even though this guy right here is not in REF because of that 2, it's going to be better because I don't have fractions. I'm still going to call those my pivots. Okay, so to put, the reason this matrix here is not in reduced row echelon form is because there are non-zero entries in the columns that have those leading ones, and I want to make this, okay, so let's just look at this one. I want to make this -1 a 0, and this 2 a 0, and this -3 a 0. Before we move on, reducing a matrix to reduced row echelon form, I don't know what's happening with the spacing here. I made the font big and it did some weird things. But this is on your definition sheet. Reduce to REF force zeros above each leading one using row operations, starting with the bottom leading one and working your way up to the top leading one. Okay. So that's what I'm going to do. Remember our pivots here? This guy was first, this guy was second, and this guy never even had a chance, so he was last. Now the last will be first, and you'll use this last one to put a 0 there, and to put a 0 there, and then this guy who was second to the last, he'll be next, you'll put a 0 there, and then this guy, you won't really need to do anything with him. So that's what I'm going to do, and I'm going to use row operations to do this. So we'll continue down here. The first thing I'm going to do is write row 3, 0, 0, 1, 6. And then I'm going to go ahead and realize that those guys are opposites there. So I could automatically put a 0 there just by adding row 2 and row 3 together. And that's going to become my new row 2. Okay, so that's what I have. So I have 0 plus 0, 0. 2 plus 0, 2. Negative 1 plus 1 is 0. That's what I want. And then 2 plus 6 is 8. Okay. Now I want to use this pivot to put a 0 there, so I'm going to have to multiply row 3 by a negative 2. Then I'll have a negative 2 there and a positive 2 there. So multiply row 3 by negative 2. So here's my modified row 3. I'm going to add that to row 1. So let's see what I get for row 1. 0 plus 1 is 1. 0 plus a negative 3 is negative 3. Negative 2 plus 2 is 0. And negative 12 plus 2 is negative 10. So here's my pivots. This guy has zeros all above it. We're done with that pivot. Now we're going to move on to this guy right here, which is a 2. Before I move on, my machine language is negative 2, row 3 plus row 1 becomes the new row 1. And any time this camera is going to stop, for some reason it wants to stop after 50-some minutes, so I'm going to be listening for a beep and continue after that. Okay, now I'm going to use this 2 as a pivot. Well, actually it's a 2 and there's an 8 there. So it looks like what I could do is just, before I do that, I think I'll multiply row 2 by 1/4. So 1/4 row 2. Ha! Not 1/4. Okay, so where's... I could do that, but I don't want to do that. Okay. I'm going to multiply it by 1/2. Okay, so 1/2 row 2 is going to become the new row 2. And we'll get another piece of paper here. So let's see how this works out. This is going to become 1, negative 3, 0, negative 10, 0, 1, 0, 4, 0, 0, 1, 6. Now, some of you may have said, well, I'll just multiply this by 3, row 2 by 3, and row 1 by 2, and then have like a negative 6 and a 6 there and do that. You could have done that. But now I have pivot here, pivot here, pivot here, and I'm trying to use this middle pivot to force a 0 above it. I'll multiply row 2 by a positive 3 to get opposites there, negative 3, positive 3, and add those two rows together. So the machine language for this is 3 times row 2 plus row 1 gives me a new row 1. So here it goes. We'll write that row 1 first. This looks like it's going to be, oh, probably should have written this below here. So 0, 3, 0, 12. That's going to be added together with row 1. So my new row 1 is going to be, what is it? 1, 0, 1, 2, and then I have 0, 1, 0, 4, just copying down the rows, and then 0, 0, 1, 6. And I did kind of a bad job here. I'll just rewrite this again because it's a little too close to the work there. Oh no, what have I done? I didn't even do this right again, look. So when I add them, look, I have 1 plus 0 is 1. Negative 3 plus 3 is 0. And then 0 plus 0, I went ahead and put a 1 there. Shame on me. Okay, because a 0 plus 0 is a 0. And then we have, I may have even said the wrong thing, and then there's a 2 there. Okay, so sorry about that. So there it is. We've just reduced the matrix to reduced row echelon form RREF, and that's pretty much what we did there. Here's the deal. We finished this problem. Remember when we did this problem again? So I'll just say 3 again on this page as well. What would have happened if I had taken this matrix and done row operations on it until I got it to reduced row echelon form? You can try that on your own. You can pause the video and then try doing that, like use the 5 as a pivot to put a 0 there, and then use this. And you'll find that you'll get exactly the same RREF. So what does that tell you, if you believe me on that, is that REF is not unique, but RREF is unique. And so it doesn't matter how you do row operations, if they ask you to put it in reduced row echelon form, you should get exactly the same answer that the book gets in the back. So that means if you are doing your homework and they ask for row echelon form, you could take your answer and the book's answer and keep going and turn them both into RREF, and you should get a complete match on that. And if not, then something went wrong. Now there's computer algebra systems like Wolfram Alpha where you can just enter a matrix in and ask it to go to RREF. So you could put the book's answer and your answer into a computer algebra system to see if you get a match. So that is how you can take care of verifying the REFs in your homework if you get something different from the book. But RREF, you should get exactly what they get because it is unique. So here's a picture that I drew, and I know this is kind of a silly picture. That we have that matrix A. There's lots of different REFs, but there's only one reduced row echelon form. Okay. So let's go ahead and do a recap on problems 3 and 4. We're going to show you something. We're kind of foreshadowing what's going to be in the next section of this book. We had this matrix. We reduced it to this. This was row echelon form, and then this is reduced row echelon form. Let me go ahead and put that REF, and then this one is RREF. Okay, now here is the deal. This matrix, let me go ahead and put lines down here. And it looks as if this first matrix is an augmented matrix. and it is an augmented matrix, the system, I'll write out the system. This is the x column, the y column, the z column. So this is 3x minus y plus z equals 8. There's the first one. And then the next row is 3x plus y plus z equals 16. So I'll write that down. 3x plus y plus z equals 16. And the last row is 2x plus 2y minus z equals 6. So you could have had a 3 by 3 linear system. 3 by 3 means 3 equations, 3 unknowns. You put the matrix, put it into a matrix, put it into an augmented matrix, do row operations until you get to REF. When you get to REF, you can stop and write out the equation. So this is x minus 3y plus 2z equals 2. The second row says 0x, so there's not going to be an x there. You'll have a y minus 1/2 z equals 1, and the third row gives me that z equals 6. Now I can solve this system by putting z equals 6 into here. So this is back substitution, and I end up getting y minus 1/2 times 6, so y minus 3 equals 1, y equals 4, and then I can plug that into the first equation also with 6, and I end up getting x minus 12 plus 12 equals 2, x equals 2. And so I end up getting 2, 4, 6. For my final answer, this linear solution is non-homogeneous because there's not all zeros there. It's consistent, and it has one solution. So it's independent, has one solution, and that solution is x equals 2, y equals 4, z equals 6, or 2, 4, 6. And when I take a linear system, write out the augmented matrix, and put it into row echelon form, and then do back substitution, this method right here is called Gaussian elimination. Gaussian elimination, I'll go ahead and I'll circle it in green. So this is Gaussian elimination. Okay, that's a little sloppy there. Well, and some of you were probably wondering about this, but what would happen if you took this system, wrote out the augmented matrix, and did row operations all the way to reduced row echelon form? Then look at the 3 equations when you read them off. X equals 2. Second row, y equals 4. Third row, z equals 6, which gives me 2, 4, 6. Okay. That actually was easier to do at the end, but in terms of work, the work was then done going from REF to RREF. This method also has a name. It's called the Gauss-Jordan elimination method. Gauss-Jordan elimination. So when we do Gauss-Jordan elimination, I'll circle this one in blue. Gauss-Jordan elimination is when you go all the way to reduced row echelon form, and then you can just copy down the answer for the most part on a problem like this. Gaussian elimination you stop right when you get to REF, write down your equations, and do some back substitution and get the same answer. Okay, so some of you will say, well, how do I know which one to use in the homework? They will tell you some of the times. Now, if they don't tell you, and you should be doing your homework by hand, you shouldn't be plugging this into a computer algebra system. So you're doing these things by hand in your homework, and they give you a choice. What I usually do is I stop at REF and do Gaussian elimination, because by the time I get here, I'm already sick of row operations, and I don't want to do one little arithmetic error and mess everything up. So if I was doing everything by hand, I would do Gaussian elimination if they gave me a choice. Now, you know, when you get a job and you're sitting at a computer and you're an engineer or whatever you're doing and you have the computer right there, you could, if you had one of these, stick that in that matrix you can write down, stick it into the computer, and then I would just write RREF as the command on the computer. The computer will do all the arithmetic. That's when I would use Gauss-Jordan elimination. So like when I was at Department of Defense and we were breaking codes, you know, you could have had like a 20 by 20 system. You wouldn't want to do that by hand. You would use a computer. The only time you would want to do it by hand is if you had to go to a really long meeting that goes for like 2.5 hours. Then you would then do it by hand, and then they would come to your cubicle and you were like, no, I'm working on this code here, and I have to finish my linear system, and you're just doing it by hand just to get out of the meeting, then Gaussian elimination, and do it by hand. So that is pretty much covering 2.4, which is called REF and RREF. Now, what I'll do is I'm gonna, so some of you might be like, okay, he's done with it. So you can turn off the video here. I'm just gonna do a homework problem. Okay, so I mean, we're kind of done with lecture. I'm just gonna do this homework problem for those of you who are like, well, I just wanna see another problem done. So I'm gonna do this. I'm only gonna do it one way. I'm not gonna do it 5 different ways. Reduce to reduced row echelon form and find the rank. So I'm going to see if we can do this problem. There's many ways. You might even pause it and see if you can do this problem yourself. When I do this problem, I'm not going to go ahead and write down my machine language on this, and we'll just see how it goes. I'm going to go ahead, or am I? Maybe I'll end up writing down the machine language. I don't know, because I'm going to, yeah, so why not? Row 1 minus, how about plus row 3 gives me the new row 1. Okay, so yeah, I'm trying to just get a 1 in the first column. I didn't have to do that, but I feel like it on this one. So 3, so we add those together, so that's a 1. And then we have a 4, and then we have a negative 11. So maybe you pause the video and you're trying to see if you're doing this, see if you can do this. So then this gives me, we just keep everything else the same. And then this is negative 2, negative 1, 1. Okay, so now what I want to do is I want to multiply row 1 by a negative 2, and this gives me negative 2, negative 8, positive 22. And so I have 1, 4, negative 11. I'm going to add this to this. So this gives me a 0, a negative 5, and a negative 15. It's not negative 15. I'm sorry, it's a positive 15. There we are. See, because 22 minus 7. And then I'm going to go ahead and there's a few things I could do. I could actually use the 1 as a pivot and multiply row 1 by a positive 2. Or what's really tempting is to add row 2 with row 3 and get that really quickly. So, you know, so I'll just write down what I'm doing here. So 2 row 1 plus row 2 gives me the new row 2. But before I do that, maybe I should just write that row 2 plus row 3. It was so tempting. I'm going to do it that way. It gives me the new row 3. So look at this. So before row 2 got wasted, I'm going to say 0. And then this right here is 2. And then this right here happens to be negative 6. Okay, another piece of paper. Okay, so what do I have here? I have 1, 4, negative 11. I'm going to scale down those rows. This is 0, 1, negative 3, and then the next one is 0, 1, negative 3. What do you know? Look at row 2 and row 3 look the same. So I'll write out my machine language here. Negative 1/5 times row 2 gives me row 2, and 1/2 times row 3 gives me new row 3. And wow, when you have two identical rows, what you can end up doing is just zeroing out the bottom row. Why? Because you really just can go row 2 minus row 3 gives me the new row 3, which is a row of zeros. So that's what I'm going to do. I have 1, 4, negative 11. 0, 1, negative 3, 0, 0, 0. In this matrix, I only have 2 pivots. Okay, I don't have a pivot on the bottom, so now it's in row echelon form. The instructions were to reduce it to reduced row echelon form, so I'm going to use this pivot right here in the middle to create a 0 above it by multiplying, let's see, multiply row 2 by a negative 4. So this is 0, negative 4, positive 12. I'm going to add that to row 1. So negative 4, row 2 plus row 1 gives me the new row 1. Let's see how that's going to work. So this gives me, let's do this. So 0 plus 1 is 1. There's a 0 there because I have a negative 4 plus 4, and then 12 minus 11 is 1. Row 2 remains unchanged, and row 3 is still zeros. The instructions were reduced to RREF. You can check the 4 conditions of RREF. They are satisfied. That is my answer. If my first matrix was called A, they want me to find the rank of A. The rank of A, that's not an R there. That's okay. The rank of A happens to be 2. Okay, so that was one of the problems from the book. Hopefully I got the right answer. That completes a very long section. 2.4. Do your homework. Have a good day.